So in today's mini lecture, I'm going to be talking about atomic structure and bonds. But before we jump into talking about atoms, I want to introduce the theory of chemical evolution. So this theory states that inputs of energy led to the formation of increasingly complex carbon-containing molecules. These molecules eventually evolved into molecules that could replicate themselves. And a descendant of this original molecule became metabolically active and acquired a membrane and became the basic unit of life, a cell. So we went from having this primordial soup, as depicted by this adapted Andy Warhol painting, to having a cell that could replicate and carry out metabolic actions. And life evolved from there. So we're going to begin this course by talking about atoms and small molecules before we jump into the cell. So let's talk about atoms. Just 4 atoms make up 96% of all matter in living organisms. And those atoms are hydrogen, carbon, nitrogen, and oxygen. We can get up to 99% if we include phosphorus and sulfur. So very few, just 6 atoms make up most of human life or animal life. To understand how these simple substances evolved into complex structures that are in living cells, we have to first consider the physical structure of these atoms and how these atoms form into simple molecules that serve as building blocks in chemical evolution. So this is probably a lot of review for you, but we're all going to start on the same page, and I'm going to go through what atoms are made of and their structure. So atoms are made of protons that have a positive charge, neutrons that have no charge, and electrons that are negatively charged. And I'll talk on the next slide of how these are arranged in an atom. But first, let's talk about how atoms are represented on the periodic table and what information we can get from that. So atoms, or I should say elements, are made up of a single kind of atom. And all the elements have a letter code. Here I'm showing carbon, that's represented as C. And there are 2 numbers on the periodic table. And they can be on the top or on the bottom, but we're going to start with the smaller number here. So the smaller number is the atomic number. This is the number of protons in an individual atom. And this is unique to each element. So if the number of protons changes, the atom or the element changes. The larger number, shown here on the top in green, is the mass number. And this is the number of protons plus the number of neutrons. In neutral atoms, the number of electrons equals the number of protons. So if we take carbon here that has 6 protons, this means that a neutral atom of carbon would have 6 electrons. Some atoms can also exist as ions that give up or accept additional electrons. And so something like this might be a chloride ion or a sodium ion. And we'll talk about this more when we talk about ionic bonds. But in general, if I don't say anything about an ion, you can assume that I'm talking about a neutral atom. Elements can also exist as isotopes. And so this is an element with a different number of neutrons. So here's carbon, right? It has a fixed number of protons, but this atomic number has changed to 13. So in this isotope of carbon, we have, instead of having 6 electrons, we have 7. And in this isotope, carbon-14, we have 8 instead of 6. And so this number can change, and in the periodic table, this number up here is usually an average of the natural existing isotopes. And this can also tell us a little bit about atomic weight. And so this is the mass of naturally occurring isotopes, and it's usually expressed as daltons. So it's just a quick look at how to process the information in a periodic table. Next, we're going to talk about how electrons, protons, and neutrons are arranged in an atom. So let's start with we call this the atomic nucleus. And this is where the protons and neutrons reside. Orbiting the nucleus are the electrons. Okay, and electrons move in these regions called orbitals. And each orbital holds 2 electrons. So these 2 electrons here are actually in the same orbital. And orbitals are then grouped into electron shells. So if we take this first shell, which we would number 1 here, this first shell can have 1 orbital, and so that carries 2 electrons. And then the next shells can hold 4 orbitals. Okay, so this is the electron shell number 2. And so they're numbered, right? Starting with the one closest. The electron shells are numbered, starting with the ones closest to the nucleus. So here's 1, and then 2. And so they're numbered out depending on how many electrons there are. The outermost shell, we call this the valence shell. And these are the electrons that can participate in chemical bonding. And so we call these the valence electrons. So that was carbon. Let's take a look now at some other atoms. And so this is figure 2.3 in your textbook. And you should be able to, if I give you maybe carbon, if I say this is carbon 12, you should be able to arrange, especially after class, the protons and neutrons in the nucleus, and then arrange the electrons in the different shells, the different electron shells, and indicate how many electrons are in the valence electron shell, or how many valence electrons there are and how many bonds can form. So let's take a look at oxygen. Oxygen has 8 electrons. So we have 2 in the innermost shell in the single orbital, and then in the outermost shell we have an orbital here that's a pair, so 2 and then 4, 6. And then these 2 electrons are unpaired. They're unpaired in their orbitals. And so these can participate in chemical bonding. So often we call this then, those that can participate in chemical bonding, we call it its valence. And so here, right, we have 2 unpaired electrons, so we can have 2 chemical bonds. In class, we're going to work through these. So when given a mass or an atomic number, you should be able to draw that atomic structure. We'll get more practice. And I'm specifically going to focus on these really prevalent elements that are shown in blue. So hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. Okay, so those are individual atoms. The next terms I want to cover are molecules and compounds. So molecules are 2 or more atoms that are joined that are chemically joined by a covalent bond. And so this could be carbon dioxide, this could be molecular oxygen, this could be hydrogen gas. A compound is 2 or more different atoms that are chemically joined. So if you take these molecules up here, the only one that would be a compound would be carbon dioxide, because there's different atoms, and here oxygen, molecular oxygen, and hydrogen gas are the same atoms. Okay, so let's talk about the types of bonds that can occur within molecules and compounds. And those types of bonds are called covalent, ionic, hydrogen, and van der Waals forces. And we're actually, in this video, not going to talk about hydrogen bonds. We're going to save that to when we talk about water. So if you're following along in the note-taking guide, you'll have to hop around just a little bit if you're following along with this video. So covalent bonds are the strongest of the chemical bonds, and they're strongest because the electrons are shared between 2 atoms. And as I mentioned before, the number of unpaired valence electrons determines the number of bonds that can form. So here we have 2 hydrogen atoms, right, that each have 1 electron. And their orbitals are unpaired, so they can each participate in a single bond. So this hydrogen gas forms a covalent bond, and these 2 electrons are shared, so they spend equal time rotating around each of these individual atoms. Okay, so we call this type of covalent bond, when the sharing is even, we call this a non-polar covalent bond. And we'll talk in later lectures about how much energy is stored in these non-polar covalent bonds. The other type of bond, covalent bond, is called a polar covalent bond. And in this type of bond, the sharing of electrons is uneven. And to really put our heads around this, we have to introduce electronegativity. So electronegativity is the strength at which atoms pull electrons towards themselves. And this is different for different atoms. So atoms that are higher, so up here, right, on the periodic table, this is just part of the periodic table, and more towards the left, right, actually more towards the right, further to the right of this table, they have higher electronegativities. So let me just, okay. Atoms that are higher and further to the right of the periodic table, so up in this area, will have higher electronegativities. And that's because their valence shell is close to the nucleus, so here, right? And they're nearly complete. Okay, so if you take fluorine, for example, its valence shell only has one unoccupied electron, and its valence shell is relatively close to the nucleus compared to something like chlorine. And so this atom is going to have very high electronegativity. And it has more electronegativity than oxygen. Oxygen is another atom that is very electronegative. And this is followed by nitrogen. And then basically the rest of the elements have about the same electronegativity. And so nitrogen, oxygen, and fluorine are going to want to steal electrons when they participate in a covalent bond. And this is depicted here in water. So oxygen, right, can form two bonds, right, two covalent bonds to fill its valence shell. So it can have a bond with hydrogen and another bond with hydrogen. But it's more electronegative than hydrogen. So the electrons will spend more time orbiting the oxygen atom than they will orbiting hydrogen. And what this does is it contributes to partial charges. So the oxygen is slightly negative and the hydrogen is slightly positive, as shown here with these symbols. And we're going to explain in the next podcast how that contributes to some really unique features of water. Okay. So we've mostly talked about single bonds, but this, like in water and ammonia and methane, for example, that's CH4. But small molecules can also form double and triple bonds. So if we look at carbon dioxide here, we have oxygen that needs 2 electrons, right? But it can actually create a double bond in which they share 4 electrons between each other. Or we can have a triple bond in which the 2 atoms share 6 electrons between each other. And so we see these in small molecules. And so this is just something to pay attention to. Sometimes this double bond is represented by 2 lines and a triple bond is represented by 3 lines. So be comfortable knowing how many electrons are in different bonds and how we might represent that in line diagrams. Okay, so that's what I have to say about covalent bonds. The next thing we'll talk about are ionic bonds. These are weaker chemical bonds than relative to covalent. And these occur between ions. So recall that ions give up or accept electrons. And so here is sodium. And sodium has 1 electron in its valence shell. And so often it will give up this electron and it will act as a sodium atom that has a positive charge. And so we call this a sodium ion. Chloride is more likely to accept an electron. So it has 1 unpaired electron in its valence shell. And so it's usually going to pick up an electron, which gives it a slight negative charge. So we have these 2 ions, sodium and chloride, and one has a positive charge, one has a negative charge, and they interact with each other, and this forms an ionic bond. The last type of bond I'm going to talk about for this lecture are called van der Waals forces. These are really interesting chemical bonds. They're talked about a little bit later in the textbook, but these are weak individual chemical bonds, but across the whole surface of a large molecule, their surface strength is quite strong because it's additive. So what is a van der Waals force? So electrons may transiently shift to one side of an atomic nucleus, and this can generate a partial charge. And so I'm showing that here. So here we have an atom, and these electrons can orbit around the nucleus, but there's a time in which these might all orbit to the right of the atomic nucleus. And this could create a partial charge where we have a partial negative charge over here and partial positive over here. And this would create an atom that could interact with another atom that is similarly the electrons are shifted to one side of the nucleus. And this creates a van der Waals force. And this force is important for things like geckos climbing up the wall, and is being exploited to invent this reusable tape that basically has all this van der Waals forces that you can stick and unstick limitlessly. And it's also important for microfiber cloths. So just a really cool chemical bond. So to summarize what I've told you, matter, both living and non-living, is made up of atoms. The atoms have a distinct structure with protons, neutrons, and electrons, and bonds form between atoms to create simple molecules that laid the foundation for chemical evolution. The bonds that we talked about are a continuum. So we have non-covalent polar bonds that share electrons equally. We have polar covalent that share electrons unequally, and then we have ionic bonds in which ions, in which they've donated or picked up electrons, form a chemical bond between each other. I also want to point out here, don't forget to view the text. There's some really nice additional animations and informations, especially if you need to buff up on your chemistry, as well as these really nice check your understanding modules, and so you can start them now. But you should definitely be able to feel like you can complete these after we meet in class. So I'm next going to talk about water, and that's it for now.